Hello everyone, I am Appala Naidu Kotana, working as a lecturer in mathematics, Dr. V.S. Krishna, Government Degree College. Today I am going to present about sequences. This topic is from real analysis. Now I am going to cover definition of a sequence and convergence of sequence and uniqueness of limit of a sequence. Finally, I will give some references. Now, we will see what is the definition of a sequence. A sequence is a map from set of natural numbers to a subset of real numbers or complex numbers. For example, if we define f as f of n is equal to 1 by e power n, here e is irrational number that is used for defining e power x, and if we define f of n is equal to 1 by I power n, here I is square root of minus 1. In first case, the codomain of the function which we defined is subset of real numbers. In second case, the codomain is subset of complex numbers. So, in the first case it is called, the sequence is called real sequence. In the second case, the sequence is called complex sequence. In any case, the definition remains same. So, again I am repeating, the definition of sequence is, it is a map from set of natural numbers to a subset of real numbers or complex numbers. If the subset is real numbers, it is called real sequence. If the subset is complex numbers, it is called complex sequence. Few more examples I am going to give. If we define f of n is equal to minus 1 power n, this sequence is real sequence. If we define f of n is equal to 1 by 1 plus I whole to the power n, this sequence is complex sequence. Other examples for sequence are f of n is equal to n by 1 plus n. Here n is natural number, that is why we are defining the map from natural numbers to subset of real numbers or complex numbers. So, the definition whatever we give here is going to valid for real numbers and complex numbers, and the theorems also they are going to be valid for real numbers and complex numbers too, but here we are going to deal with real numbers only. Usually the sequence is denoted by a n or s n instead of denoting with f of n. So, another example we can see, f of n is equal to minus 1 whole to the power n by n. This is another example. This is real sequence, and one more example we can see is f of n is equal to sin n, and few more examples if we see like that, f of n is equal to n plus 5 n square divided by 2 n plus cos n. All these sequences are real sequences. Similarly, we can define complex sequences too. Now, let us see what is the convergence of a sequence. So, the convergence of sequence is defined as like this. As I already mentioned, sequence usually is denoted with Sn or An. So, let us say Sn is a sequence for time being so we will stick to real sequence. So, the definition is like this: a sequence is said to be convergent to a limit L if for a given epsilon greater than 0 there exists m belongs to n such that modulus of Sn minus L is less than epsilon for every n greater than or equal to m. It is denoted by limit n tends to infinity Sn is equal to L. A sequence, it is said to be divergent if it is not convergent. So, here we have to note down that epsilon is given, epsilon greater than 0 is given. For a given epsilon, we have to find m, a natural number that is dependent on m, epsilon. So, m value depends on epsilon. Whenever we choose epsilon, the m value has to be corresponding to that epsilon. So, that m value should be such that mod Sn minus L less than epsilon. So, the meaning of this is mod Sn minus L less than epsilon means Sn minus L should lie between minus epsilon and epsilon. This means Sn should be between L minus epsilon to L plus epsilon for every n greater than or equal to m. This is definition of convergence of sequence. Let us see one example, from that we can understand. Now, let us see example for convergence of a sequence. Let us take Sn is equal to Sn is equal to 1 by n. Now, what we have to find is that, like, does this sequence converge really? So, claim is that limit of 1 by n as n tends to infinity is equal to 0, that is the claim. So, according to definition, what is Sn? Sn is 1 by n and L is 0. So, in definition what we have mentioned is that given epsilon greater than 0, given epsilon greater than 0, we need to find m natural number such that mod Sn minus L less than epsilon for every n greater than or equal to m. So, for any given epsilon we have to find m. So, here we have L Sn. What does this mean? Like 1 by n minus 0 should be less than epsilon for every n greater than or equal to m. What does it mean? Mod 1 by n less than epsilon. This means 1 by n less than epsilon. So, in modulus we have 1 by n. 1 by n is positive, as n is natural number, 1 by n is positive. This means 1 by epsilon less than n. So, we brought epsilon this side and n that side. This means we have to find an integer such that it is greater than 1 by epsilon. So, by Archimedean property this is possible. Archimedean property says that for a given real number we can choose natural number which is greater than that real number. Using that criteria, if we choose a natural number greater than one by epsilon, what is going to happen? Let us see. So, that is what I have mentioned here. Both are same, m greater than 1 by epsilon or 1 by epsilon is less than m, both are same. So, if we choose a natural number which is greater than 1 by epsilon, what is going to happen? 1 by m is going to be less than epsilon. So, whenever n greater than or equal to m, what is going to happen is 1 by m is less than one by n is less than 1 by m. So, we have chosen m such that 1 by epsilon is less than m. So, from which we get 1 by m is less than epsilon. This is true for any n greater than or equal to m. So, here for a given epsilon, our task is to find a natural number that is greater than 1 by epsilon. For example, epsilon is given as, for example, if we take epsilon is equal to 0.1, what is the possible value we have to choose for m? 1 by epsilon is 1 by 0.1, which is 10. If we choose any integer that is greater than 10, this relation is going to hold. Similarly, if we take epsilon is equal to 100, so what is the integer we have to choose? 1 by epsilon will be 1 by 100, this is 0.01, which means like any integer greater than 0.01 is going to be any natural number that is greater than 0.01 is going to work. That is like for any n greater than or equal to 1, the relation is true. Usually epsilon is chosen very small. In such cases, we have to choose integer carefully. Let us see. Let us go to next slide. So, Now we are going to see some properties of sequences. One important property of sequences is that if it converges, the limit of that sequence is unique. That is what we are going to prove now. So, it is a theorem. So, the theorem says that the limit of a convergent sequence is unique. Let us take a sequence Sn which is convergent to L. Suppose it converges to two limits, what is going to happen? Let us see. If the sequence has two limits, say L dash and L, and both are not equal. If both are not equal, let us define epsilon modulus of L minus L dash. Since they are not equal, the difference is going to be non-zero number. Modulus of the difference is going to be positive. So, by definition of convergence of a sequence, Sn is convergent to L. That means, given epsilon greater than 0, there exists integer m1 such that mod Sn minus L is less than epsilon by 2 for every n greater than or equal to m1. Similarly, since Sn is convergent to L dash, there exists m2 belongs to n such that mod Sn minus L dash is less than epsilon by 2 for every n greater than or equal to m2. Now, let us take m is equal to maximum of m1 and m2. So, what is going to happen now? Since m is largest of m1 and m2, modulus of Sn minus L is less than epsilon by 2, as well as modulus of Sn minus L dash is less than epsilon by 2 for every n greater than or equal to m. Since m is maximum of m1 and m2, both equalities, this equation 1 and equation 2 both are going to hold. Now, epsilon we have defined as mod L minus L dash. So, we will do some kind of algebra here. We add Sn and subtract, so that epsilon is equal to L minus L dash modulus will remain like that. So, this whole thing we can view as modulus x plus y kind of thing. So, we have an inequality, this is less than or equal to mod x plus mod y. Here x is L minus Sn, y is Sn minus L dash. So, this epsilon is less than or equal to L minus Sn modulus plus Sn minus L dash. We already have modulus of Sn minus L less than epsilon by 2. So, mod Sn minus L is same as mod L minus Sn. This is epsilon by 2. Similarly, mod Sn minus L dash is less than epsilon by 2. So, this is less than epsilon by 2 and this is less than epsilon by 2. So, together what we are going to get? Epsilon is less than epsilon by 2 plus epsilon by 2, which is epsilon. So, epsilon less than epsilon, this is greater than 0. So, a number is less than itself, this is contradiction. So, this contradiction arises due to assumption of L dash is not equal to L. So, therefore, if a sequence converges to a limit, so the limit is unique. What are its implications? Suppose we want to find the limit of a sequence, it is enough to find one limit. So, or some subsequence of a sequence limit also sufficient to find, that is going to make sure that the sequence is converging to that limit. Now, let us see that let us prove that every convergent sequence is bounded. This is another property of convergent sequence. Here also by using definition only we will prove. Let Sn be a convergent sequence and L be its limit. L is sequence limit. According to definition of convergent sequence, given epsilon greater than 0, there exists m belongs to n such that mod Sn minus L is less than epsilon for every n greater than or equal to m. So, this is definition itself. Now, let us take epsilon is equal to 1. So, epsilon is in our hand, whatever value we want to take we can take. So, for this epsilon there should exist an integer such that mod Sn minus L is less than epsilon, epsilon is equal to 1 for every n greater than or equal to m. This means the sequence Sn is between epsilon minus L and epsilon plus L. So, here epsilon is 1 or L minus epsilon and L plus epsilon. So, L is limit L minus 1 and L plus 1 for every n greater than or equal to m. Let us take k1 is equal to minimum value of S1, S2, so on Sm, and then L minus 1. L minus 1 is lower bound to Sn for n greater than or equal to m. S1, S2, S3, so on Sm and L minus 1. K2 what we will take is that same maximum of S1, S2, so on Sm and this upper bound we will take. Now, what is going to happen? Sn has to be less than K2 and greater than K1. This has to happen for every n. For n greater than or equal to m, this happens. Other cases we assume minimum value, we have taken minimum value from S1 to Sm along with its lower bound. Because of that, Sn cannot come below K1. Similarly, since we have taken K2 as maximum value of S1, S2, Sm and the upper bound value for n greater than or equal to m. So, Sn cannot exceed k2. Hence, Sn will be less than or equal to k2, greater than or equal to k1 for every n. So, this is boundedness of the sequence. So, the implications of boundedness of sequence is that any convergent sequence if we take, so it will remain within some bounds, that is what we are going to, we have proven. Is the converse true? What is the meaning of converse? Is the bounded sequence converges? Let us see one example. Consider Sn is equal to minus 1 whole to the power n. The first term of the sequence is n is equal to 1 means minus 1 whole power 1, minus 1 whole power 2, minus 1 whole power 3, so on. This means minus 1, plus 1, minus 1, so on. This is certainly sequence, real sequence. If we see the maximum value of this sequence, it cannot go beyond 2 and it cannot come down beyond minus 2. However, this sequence is not convergent, because if it converges, the limit has to exist. One case, like if we take even sequence, if we take S2n is equal to, what is going to happen, or S2k minus 1 power 2k, this is plus 1. This is one subsequence of the given sequence. Odd sequence if we take, minus 1 power 2k plus 1. This is minus 1. So, it is known that if a sequence converges, its subsequence also converges to same limit. Here even sequence is converging to plus 1, odd sequence is converging to minus 1. Hence, the sequence defined by minus 1 power n is not convergent. So, thank you. These are some references which I used to prepare this material. One is Bartley and Sherbert. This book is useful for undergrad studies. Another is Walter Rudin, Principles of Mathematical Analysis. This book is PG level book. This N.L. Karothar's Real Analysis book. This is also one nice book. This is generalization for real analysis it contains. Thank you.